You open a repository, and there it is, the AGENTS.md or CLAUDE.md file. It sits in the root directory of modern AI coding workspaces. We invest hours writing these files. We dictate architectural constraints, outline error handling conventions, and curate workflow guidance. The logic is straightforward. If we give the agent strict, highly curated instructions, it will write better code. But rigorous empirical testing reveals a problem with this logic. When evaluated under strict laboratory conditions, the expected improvements disappear. We have to ask whether the immense effort spent drafting and maintaining these context files is actually increasing task pass rates or simply giving us an illusion of control. The academic literature on this topic has been fractured. In 2026, Lula and colleagues published findings showing that Codex family agents received a measurable efficiency boost when context files were present. Later that same year, Glogan tested Claude family agents and recorded 0 significant improvements in task correctness. You cannot reconcile these two papers. The researchers varied 3 parameters at once. They tested different agent families, they used different evaluation methods, and they applied different levels of experimental control. With all 3 variables moving simultaneously, isolating the cause of the disagreement is impossible. Catri's 2026 study holds these variables constant. By examining this ablation study, we can measure the actual impact of context on pass rates and look at the mechanistic reasons why agents struggle. Solving this contradiction establishes a clear boundary for engineering allocation. It identifies where time spent on optimization is likely to yield a result and where it is likely to be lost. This grid maps Catri's independent variables. 3 injection strategies, none, always on, and selective, are tested across 2 frontier agents, Claude and Codex, deployed across 3 distinct Python repositories. By running each task against all 3 strategies with 3 independent repeats, every individual task acts as its own control. Task difficulty is held mathematically constant. The evaluations run on the SWE-bench Tier C protocol, drawing tasks directly from real merged pull requests. Tier C operates as a blind oracle. The agent is provided the pull request description and the base commit, but it never sees the hidden test suite used to grade its code. To prevent the model from gaming the evaluation, the environment relies on extreme isolation. DNS requests to GitHub are blackholed, future commit history is pruned, and Git push commands are denied at the system path level. The agent cannot cheat by reading the answers from the Git log or the internet. This defense in depth strips away the noise, ensuring that any variance in the pass rate is purely a result of how the context was injected. This minimalistic table displays the results of 288 runs. For Claude, pass rates are 53, 55, and 55%. For Codex, 58, 56, and 52%. An omnibus permutation test yields a p-value of 1.00 for Claude, implying no statistical effect. But this scatter plot reveals a trap. Almost all data points violently cluster at the absolute top or bottom of the y-axis. This is the floor-ceiling effect. Because nearly every task is either trivially easy for the agent to solve every time, or impossibly hard so it fails every time. There is almost 0 variance to permute. The p-value of 1.00 is a mechanical artifact of the data structure, not independent proof of a null effect. To establish a true null, Catri relies on 3 pillars. The first is tossed equivalence. This tests the margins, mathematically bounding any possible effect size to less than 10 percentage points for Claude and less than 15 for Codex. The second pillar targets the borderline subset, the rare tasks that actually possess dynamic range, where the agent sometimes passes and sometimes fails. On these specific tasks, providing no context file actually beat the context strategies, 58% to 42%. Proving a null in language model evaluation requires this specific triangulation. You have to measure the dynamic range and bound the equivalence. Trusting a single, easily manipulated p-value will lead you to false conclusions. If the context strategy doesn't move the needle, we need to understand the mechanism. Why doesn't reading a detailed style guide improve the generated code? These 4 cards represent near-miss failures found in the study: deficits in engineering precision, pattern choice, exact wiring, and type reasoning. Look closely at the division. The failures on the left represent missing implementation skill, An AGENTS.md file on the right only provides repository knowledge. A static Markdown file cannot teach an agent how to proactively refresh an authentication token instead of reactively retrying it. It cannot execute deep type system reasoning. The agent often reads the rule perfectly from the codebase, but lacks the engineering precision to wire it correctly. A pre-registered manipulation-validity probe confirms this. Researchers ran the models on the closest near-miss tasks. The presence of the context file actively perturbed the agent's behavior, meaning the model read and processed it. Yet across 18 iterations, Codex failed 18 times. The file never converted a near-miss into a pass. The industry is attempting to fix a capability ceiling with a data injection tool. That is a mechanical mismatch. This leaves one unresolved variable. If the context file doesn't bridge the skill gap, why did the previous 2 studies report conflicting results? This scatter plot compares Claude's pass rates on the x-axis against Codex's on the y-axis. The strong positive diagonal shows a Spearman row of 0.75. But focus on this central intersection. This is the informative band. It contains the tasks that sit neither at the floor nor the ceiling. This is the only place an experimental manipulation can register an effect. While general difficulty transfers, the informative band does not. Roughly 40% of the tasks are borderline for exactly one agent. A perfect testing ground for Claude is often trivial or impossible for Codex. The prior single-agent studies drew tasks that landed in different agents' borderline bands. They sampled different slices. This 30-point effect 57% of the time. Adding more repeats to a floor or ceiling design does almost nothing to improve statistical power. Reducing the variance inside that cell will not manufacture dynamic range. To detect a 10-point effect at 80% power, you must add tasks, scaling the evaluation to between 120 and 200 tasks. Evaluating coding agents on small, single-agent calibrated task sets guarantees underpowered, deceptive null results. The engineering takeaway is highly scoped. Generic style guide context files do not measurably improve coding agent correctness. Reallocate your engineering effort. Spend less time on Markdown files and direct resources towards task decomposition, advanced tooling, and example-driven prompting. There is one operational nuance. Context files can alter how an agent works, for example, teaching it to avoid running a slow test suite. That efficiency earns the context file a place strictly for cost and latency optimization, not capability. Relying on context files to drive agent correctness is a categorical error. Improvement on this frontier requires addressing implementation skill directly.